My name is Ethan. Currently, I'm a postdoc. I'm very glad to attend this interesting virtual meeting online. In the first page, I quote a poem from my favorite poet, Wisława Szymborska. Actually, by the way, I just found this fact, surprisingly, just yesterday, that Szymborska exactly studied in this university, the Jagiellonian University, in the year of 1945. I didn't know this before. And this poem is entitled "Under One Small Star," and she says, my apologies to Greek question for small answers. So the testing general relativity with the gravitational wave is a grand question, and this presentation is my small effort to trying to address this question. But before introducing my work, I would also like to introduce the team I'm in, the compact binary coalescence team in the Albert Einstein Institute, particularly advertising this software called PyCBC. So we are a team that used to be part of the LIGO and Virgo collaboration, but we decided to exit the big collaboration after the discovery of gravitational wave become routine. So now we are focused on independently analyzing LIGO Virgo's open data with this open source software called PyCBC. So this is the software that can do search, can do parameter inference. It is fully open source and it is maintained in GitHub. Anyone can welcome to use it and can submit modifications to this software. And if you are interested, take a look at this website, pycbc.org. And our team also released the so-called first OGC and 2OGC, which is Open GW Catalog. So the right figure is just an example of the parameter inference result for the first gravitational wave events, GW 1509.4, in this website. So if you are interested, take a look. So this work is also showcased an example of using this PyCBC software to do open data science. So firstly, I think it would be beneficial to give a brief overview of testing general relativity with gravitational wave by LIGO and Virgo. To start, so firstly, the gravitational wave waveform in the frequency domain is essentially just a mathematical formula. So this is the observable h, and it is proportional to the so-called chirp mass to the power of 5/3, inversely proportional to the luminosity distance. And this phase term is just a series expansion calculated by some techniques like the post-Newtonian perturbation. And there are some coefficients before the frequency to some power, the phi0, phi1 at all. And the red figure is just a schematic visualization of the real part of this wave with respect to frequency. So then given the waveform, how to do the testing general relativity. So there is a methodology, the so-called model independent test used by LIGO and Virgo. So if I collectively refer all the coefficients to be the P sub I of GR, then I can artificially introduce a fractional deviation of this PI. So the non-GR coefficients equals to the 1 plus delta times this PI calculated by GR, and that gives me the non-GR correspondence of this parameter, and I can, with the gravitational data, I can infer the value of this delta PI. If this delta PI is 0, then the GR is correct. If not 0, then something interesting happens. So this figure is a possibility posterior distribution of all this delta PI published by LIGO and Virgo. And one remarkable result is that you can see I draw a horizontal line marking the 0, and you can see the 0 is well within all the possibility distribution, which means that, okay, GR is correct. A second way is the so-called Lorentz invariance violation. So the conventional, so this method modified the dispersion relation of GR. So the dispersion relation of GR is energy equals to momentum times speed of light, E equals to PC, and use term, which is the power law of the momentum. So, and there is an amplitude, capital A, and there is a power index, small alpha, and alpha takes different integer or half integer value. And again, with the data, and one can infer the value of capital A. If the capital A is 0, then GR is correct. And currently, is all the data are consistent with GR, so people put an upper limit on this amplitude. And notably that this alpha equals to 0 refers to the massive graviton, which is not Lorentz evaluated, but the massive graviton. And this is the Lorentz invariance violation. Okay, so these are the two examples. So in my personal view, I would roughly classify all the current existing testing GR with testing GR with gravitational wave into 3 classes. The methodology into three classes. The first one is the model independent tests. The examples are the 2 methods introduced in the previous slides. So the second one is model specific test. So if you have a specific model like this Einstein-Dilaton or dynamical transcendence gravity, you can, if you have a well-calculated waveform, again, you can compare your waveform with the data and to constrain this specific models. So a third way defined by me is a semi-model independent test, which is the so-called effective field theory methodology. So that is the focus of this work. So this presentation, in my work, I focus on the possible propagation modification due to the parity broken of general relativity. So here, by parity, I mean the symmetry broken between the left and the right-handed polarization states of gravitational wave. Okay, so it's natural to start with an action. Here, I write down the linearized action for the gravitational wave propagation in the FRW universe in the general relativity. So here you can see here that this HIG is the tensor perturbation and also the gravitational wave. So with the action, we can derive the equation of motion. It's in this form. Yeah. And note that the subscript capital A equals to either left or right, which are the eigenstates of the propagation modes. So here, one thing I want to say is that the left and right circularized states both follow the same equation of motion, which means that their dynamical behavior are the same. But how about the non-GR? So from a point of view of effective field theory, I can continue to write down more terms with higher derivatives. So to the leading order, the modification is from 2 terms with 3 derivatives, right? So here, this small c1 and c2 are free parameters to be determined by a specific theory, and this capital M sub PV, standing for parity violation, is a energy suppression. That's roughly speaking, this is the energy threshold that above which parity violation starts to play a role. And this is a typical parameter in the effective field theory framework. And our work is very, I'm interested in constraining this energy scale MPV. Okay, again, with this action, I can derive the equation of motion. But here, remarkably, it introduces 2 additional terms, this mu A and nu A. And remarkably, that for different polarized states, which means that when A takes different values, which are either left or right, then this nu and mu takes different sign. So one positive, another negative, which means that the left-handed, which means that this time the left-handed, the right-handed gravitational wave follows different equation of motion. And their behaviors are different. So that is the so-called birefringence. And that birefringence provide additional modification to the standard GR waveform. Here I denoted by HGR, and times the non-GR is equals to GR times an additional modification. The first part is the 1 plus this thing is the amplitude modification, and another modification happens in the phase term. And this phase term is caused by the velocity difference from left and right-handed polarized states, which means that if different states propagate in different speed, then so ultimately the overall effect is that this that will provide a extra phase modification, and this is the this delta H is the amplitude birefringence. And again, you can see that this rho A takes either plus or minus 1 for different polarized states. So that is what I mean by the parity broken. And also very interesting effect is that this effective field theory with leading order tensions to GR can be mapped to the best of my knowledge, can be mapped to all the existing specific modified gravity models in the market. So in this paper, we have a dictionary of this map. So if you are interested, you can take a look at this paper. Okay, but the left and right-handed polarization states are not usually used in the data analysis of gravitational wave. What is used more often is the plus and cross polarization. There is a simple conversion from each other. And another fact is that this delta H, if you remember this is the amplitude modification, is negligibly small to the phase part. So so this can be negligible. So the only surviving term is this delta psi. So this delta psi equals to this amplitude A mu times the pi f as the frequency divided by Hubble parameter, and this A mu is just a pure auxiliary parameter for the convenience of the data analysis. And this is A mu is related to the truly interesting parameter MPV by this conversion. So it is equals to the MPV inverse times a cosmological term. So now we have the waveform with leading order modification to general relativity. We also have the open data from the Kennelly, LIGO, and Virgo collaboration, and then we can compare our waveform model and the data, and to see whether the data is more consistent with GR or more consistent with the parity violation waveform. We can perform the gravitational wave parameter inference and estimate this capital A mu. So in this slide, I show the results of the inference of A mu with 12 gravitational wave events. At the moment when this work was done, these 12 events were released. And all these so-called violin plots are the posterior probability distribution of each event. And again, you can see that 0 value of A mu is consistent with all the data, which means that, okay, the GR is again correct. So with this conclusion, we can thereby we can put an upper limit on this amplitude A mu parameter. And from this result, we can have more physical insight, which is you can see that there are a few events that performing better than other events. For example, this so-called GW151226 and GW170608, these two events, and the two binary neutron star events, their behavior is better, and the reason is reasonable because their mass is relatively lower, so that their waveform is longer. The duration of waveform is longer than other effects. You can see that this is a visualization of the energy versus frequency of the gravitational wave events, you can see the two longest waveform exactly comes from the two event that gives the best constraint on the A mu. And the reason is that if you have a longer waveform, then you can resolve the more subtle structure of the waveform that gives better constraint of any possible deviation from the modification. As I said, that the A mu is just a auxiliary parameter, and to convert the A mu to MPV is also straightforward. In this slide, I plot all the results for the estimation of MPV for different events, and all the colorful lines are the individual GW events, and the black solid line are a combination of all the events. So if every events do not have a violation of GR, then if you combine them, you can get a tighter constraint of this MPV, and which is the black line. And you can see that the 90% upper limit for this energy scales inverse is this value, which means that the lower value of MPV must be larger than this 0.09. Remarkably, the unit is giga electrovolt. So this is high energy. It's relatively high energy. I also compared my results with other existing results in the market. So this is the result from this research, the constraint from the gravitational wave catalog, and that is the 0.09 giga electrovolt. And there are also other constraints, like the constraint from solar system, from the binary pulsar observation, from the gravitational wave speed measurement, from the binary neutron star events, and there are also forecasting results from the gravitational wave polarization, and this is a comparison of each result. So the previous slides show the results with the existing data. And so from the earlier two talks, you probably know that there are also a very promising future for the gravitational wave astronomy and detectors. You know, the LIGO Virgo constantly upgrading towards the design sensitivity. There is Kagura in Japan joining the global network, and there are also so-called 2.5 generation design, LIGO A+, Voyager. There are also third generation detectors projection, Cosmic Explorer, Einstein Telescope. In this figure, I plot the theoretical expectation of the noise amplitude of different detectors configuration. And you can see compared with the let's pick the LIGO design to be the blue curve, and compare with the blue curve, you can see the future Cosmic Explorer and Einstein Telescope further improve this result with 1 order of magnitude, which means that we can see 10 times further in the distance, which means that 1,000 times larger in volume. Okay, so I used this proposed future gravitational wave detectors to also perform some mock data analysis. So I inject 200 gravitational wave sources and into each configuration of gravitational wave detectors. And these 200 sources, spatially they are uniformly located in every direction, and their distance is up to the 2 gigaparsec. And for the third generation, because it can see further, I pick the 5 gigaparsec. And all the 200 sources are binary black holes, and their masses are uniformly distributed in the 5 to 50 solar mass. And this is the result. Second thing is that I also choose the signal to noise ratio to be larger than 8 to be a detection threshold, which means that only those with larger SNR can be detected. That is natural. So this figure basically shows the result. There are 4 choices of detectors: the 2G design, which means a LIGO Virgo Kagura network, and that's also substitute the detectors in 2G with A+, substitute those with the Voyager. And for the 3G, I mean the Cosmic Explorer Plus and Einstein Telescope. And this figure basically shows all the results. To analyze this figure, firstly, we can an interesting effect is that among these 200 sources, for the 2G design, which is the red curve, only roughly 80 sources have SNR larger than 8. Okay, and for the A+ configuration, that number increased to 100 and roughly 30. And for the Voyager, this is increased further. And for the third generation, even I choose the upper limit of the distance to be 5 GPa/sec, all the 200 binary black holes can be detected with the third generation. So that is also a proof that the third generation is very promising to resolve almost all the binary black holes in not only the local universe, but in the cosmological distance. And you can see that with the second generation detector, and so it can, with one event, it can roughly constrain the MPV inverse to be 0.0 something MPV, and as the accumulation of the number of events, and it increased to this value. And remarkably, for the third generation, and with one event, you can constrain it to be a giga EV level, and with the 200 sources, it reached to the 10 giga EV level. And from some rate or population analysis, the third generation is expected to detect 10 to 5 sources up to 5 GPa. So that can further improve the constraint to be one order of magnitude larger, which is the 100 giga EV. Okay, so to summarize, so firstly, the gravitational wave, the existing gravitational wave data can already put some interesting constraints on the parity violating energy scale at the GeV scale. So compare with particle physics, this is not that high, but if you compare with other previous constraints for gravity, like the test from solar system, this is already relatively high energy regime. And a second thing I want to say that testing general relativity with effective field theory has a clear physical meaning. In this work, we constrain the MPV, which is the energy suppression in this parity violating effect. But for model independent test, although we it's perfect that we do not find the violation of GR, but it's hard to interpret the physical meaning of your result for each constrained result. And the third thing is that all this work has utilized the open source software PACBC and the open data released by LEGO Virgo collaboration. And I also released all of my scripts and posterior results in my personal website. And I would like to, motivate and facilitate this open data gravitational wave science, because after all, it's very interesting and there's very promising future. Okay, I would stop here and would be happy to take any question.
Okay, yeah. Let's unmute the microphone and let's thank Yifeng Wang for his nice speech. All right, now we have actually a couple of questions. We have a couple of minutes for questions. Why I can see myself?
Yeah, sorry, but yeah, if I don't do this, I cannot see the chat box.
I see. Okay, actually, I have any questions? If no, then I will ask a question.
Sure, please.
Yeah, I mean, if I understand correctly, there are two types of parity violation. One is from source term, like this FF2, the one mentioned by Giamassimo in his talk. Another one is an intrinsic parity violation from gravity sector itself. Observationally, how do we distinguish these two types of violation?
Okay, I'm not sure I fully understand your question because I'm not from the theory side. But my feeling, one thing in my mind is that I want to emphasize is that in this work, I only considered the possible propagation modification of the gravitational wave, which means that when the gravitational waves are generated by the binary black holes, and there's no modification of GR when they emit the gravitational wave. All the modifications only happens when the gravitational wave propagates in the space-time, in the universe. So the two types you mentioned, or the intrinsic thing. So basically, I think my feeling is in this work I cannot distinguish because I do not consider one of your possibility or both possibilities. So it's possible that both of your two types of modification are ignored by this work, maybe, but I'm not 100% sure.
Hi, Giamassimo, are you online?
Yes.
Do you have any comments? The different observational difference?
It's a good question. I don't know. I don't think that, because when you detect gravitational waves, if they violate chirality, I don't see immediately any way besides additional effects that can be around. But from the measurement of chirality alone, I wouldn't know whether it comes from an FF tilde or from this kind of parity violating sources or from intrinsic. Of course, you have to think about, okay, when you say intrinsic, of course, GR doesn't violate parity. You have to add some additional field in order to violate parity. For example, a scalar, and you consider couplings like phi r tilde. Yeah. Where R is the Riemann, I say is a contracted phi r mu nu rho sigma r mu nu rho sigma tilde. So you could consider these kind of operators, but I wouldn't know from the measurement of chirality violation alone in the gravitational wave sector how to distinguish. Of course, there might be other effects. There might be other effects not only associated with chirality, I don't know, some properties or the other properties of the signal can tell you, but I don't think that this kind of question have been studied.
Yeah, but I think it's worth it to think about this.
Yeah.
All right. Do we have any other questions from audience? Okay, if there's no more questions, let's thanks all speakers in the morning again.